So this is our second lecture in Chapter 3. Chapter 3 deals with one-dimensional steady-state conduction. Last time we focused a lot on the wall in a plane coordinate system or rectangular coordinate system, just heat transfer through the wall. We're able to take our governing differential equation and boundary conditions and solve for the temperature as a function of position. It's a line, a constant slope through the wall. And we are able to come up with a thermal resistance, L over Ka. So L is the thickness of the slab, A is the area through which the heat is flowing, K the thermal conductivity. Then we were able to put together slabs in series, like a composite wall, as well as putting these resistors in parallel, so making a thermal network just for conduction. Then we had contact resistance, R thermal contact, double prime funny units. Pay particular attention to the contact resistance. This would basically skip the porous media, but it's effective conductivity. Give me an effective conductivity when I have a mixture of materials, maybe a solid with gases interspersed, or two liquids, or two different solids. So we're also going to basically skip the alternative conduction analysis. It's pretty straightforward, but moving forward, we need to get into radial systems today. So we have the cylinder, the wall, so to speak, as like insulation, a layer of insulation around a pipe. We'll be able to solve for the temperature as a function of the position R through that layer, and then get a thermal resistance. Likewise, it's hard to draw in 2D, but a sphere and a spherical layer in that layer of insulation, so solve for the temperature as a function of R now in the radial, and get the thermal resistance formula for one-dimensional conduction through that insulation layer. Then we're going to talk about when you have heat generation, Q dot, and in a wall we get a quadratic or a parabolic shape to the temperature as a function of location, T as a function of X. And then we also can solve for temperature as a function of R in a rod, cylindrical, as well as spherical coordinate systems. In appendix, they tabulate a bunch of results. Setting up and solving differential equations is the theme of this lecture, just like it was last lecture. And then we're going to skip this concept where you could think about a thermal resistance when you have heat generation in the slab. It gets a little more confusing. I just skip it. Okay? Let's press forward. So we have this pipe. Here you can see this is a copper pipe, thin-walled, and it has a layer of insulation wrapped around it. A lot of times we look at it on the end. There's the center. There is the inner radius, R1, and then you have a layer of insulation going out to R2. We're interested in how the heat flows through that insulation. So maybe it's high temperature. Let me try and draw a temperature this way as a function of R. Temperature is a function of R. And we're really only interested in R between R1 and R2. Just in this location right there between R1 and R2. And maybe it's high temperature right there having a magnitude TS1, the surface temperature at 1, or just call T1. You can drop the S, too many subscripts. Just call it T1 at R1. And right here it's at T2 at R2. And we want to solve for the temperature distribution right in there. What is T as a function of R? R going between R1 and R2. How do you solve for it? Well, we set up the governing differential equation for heat conduction. No heat generation, so Q dot 0. And it's steady state. And so it boils down to 1 over R, derivative with respect to R of R dt, dr, equal to 0. It's second order. Hence, we need two boundary conditions. So boundary conditions are T at R1 is equal to T1, and the T at R2 is equal to T2. It's both specified temperature boundary conditions. All right. What's the strategy? Good differential equation, two boundary conditions. You separate and integrate. You separate and integrate, then you do it again, separate, integrate. You have two constants of integration. This one is a little more tedious, a little more mathematically, need to be on top of it and watch out for errors. You need to pay attention to signs, but it's all within your capability. So I'm going to use a four-letter word here and just say work. You can do it. And you can get that the temperature distribution T as a function of R is equal to the T1. And then what we're going to have is the minus the T1 minus T2. You have the natural log of R over R1 divided by the natural log of R2 over R1. All right. The next thing that you want to do is you want to get the rate of heat transfer Q through, once we solve for the temperature distribution, we want to get the rate of heat transfer through that layer of insulation. Well, would we use Fourier's law? Sure. Fourier's law would be minus K A dt dr. All right. dt dr. And A, I want to spend a little bit of time on. All right, let's focus on A first. A. For this problem, clicker question, the answer either A or B. The area of interest, is that going to be either, I'm going to do this one, pi R2 squared minus R1 squared? That would be answer A. Or is it going to be for the area of interest 2 pi R times L? So let's go ahead and see what you think. I'm looking for an equation for this area A. Let's have a little discussion right here. If I cut this and I cut it, let's say I take a saw and I'm just cutting, and I keep moving back in that direction, cut and cut and cut. Isn't that the direction for L? The length of the pipe? That's what that L means right here. I purposely didn't emphasize what L was, but I'm thinking it's the depth or the length of the pipe, right? And so if I cut it here and I cut it there and I cut it there and I cut it there, then I flip it and I take a look. This is the cross section looking at it, right? And so I know it's hard to visualize all this. Some of you get it very easily. Some of you struggle with visualizing it. And then what we're trying to do is sketch the temperature profile in that layer where it's high at R1. That's easiest to think about, I think. It's high on the inner temperature, inner surface, and lower at T2 is lower than T1 at R2. And so this is the profile right here. So somebody says this area here is the area perpendicular to the direction of flow. How is it flowing? It's flowing that way, isn't it? From the hot copper pipe to the air on the outside through the insulation, isn't it? So let me ask the question again. What is this area in the Fourier's law? Is the best answer A or the best answer B? Same question, another shot at it. Now let's say that I had my pipe, I'm going to redraw it like this, and this is the intersection right here, and that intersection goes further back, And somehow it was hot on this end right here. And I know it's hard to see, but it's cold on that end right there, right? Do you see that? And what direction would the flow of heat be? Down the length of the pipe. And in that case, what would my area be? Would it be pi r2 squared minus r1 squared? Or would it be 2 pi rl? This, now I changed it up a little bit. It's not going, the heat transfer is not radial, it's axial. What would be the correct area, A or B? For that second case, it's as if this outer layer was insulated. And it's as if the inner pipe was all insulated. And then it's actually hot on one end and cold on the other, and it's just axial heat transfer going down. So in that case, that's the last question I posed, isn't this the correct area for that the heat is flowing through? Right? Down the pipe. Okay, but now we go back to the second question. And the second question, we wanted a higher percent correct, but this is the radial heat transfer, right? Radial going out. And so it's B is the correct answer. And the first time I asked the question, so I was hoping I would add more discussion and then re-ask the question and get a higher percent correct. But sometimes when the faculty talk more, they only confuse the poor student more. So that one backfired on me. But this area is a function of the location R, radial, going out. And it gets larger and larger as I go further and further out. It's 2 pi r times L. Let me ask this. The TDR, is that a constant? No, it's not a constant. Not a constant. It's a function of R, right? But what about this Q? What exactly was Q? Oh, let me ask this clicker question. Are the units watts, watts per meter, or watts per meter squared? Answer A, B, or C. What are the SI units of Q for this problem? All it is Fourier's law. Let's go ahead and look at the results. So that's pretty good. We're not 100% correct, but it's hard to be 100% correct. It's easy to get a little confused. But Q is our rate of heat transfer in watts. It's going from the inner copper pipe, in this sketch up here, to the outer layer of the insulation. So through the insulation, radially. Okay, so this is the units in watts. Let me ask this question. Is Q a constant, or is it a function of R? Is Q a constant? Should that be a clicker question? Okay, Q, is it a constant, let's say 25 watts, or is it a function of R, R being the location, radial location as I'm going out through the insulation? Answer A or answer B? Well, let me just show the results. What? Q. Okay, I can't grade that quite yet. Close this. Let me insert new page. All right, so I have, it's hard to show, but I'm going to show in 2D a control volume. The control volume looks like a donut. There's inflow on the inner surface of the donut, and there's outflow on the outer surface of the donut, and the length of the donut looking in the third dimension, kind of sketched that way. L, pick it to be just 1 meter length. Just standard, one length into the board. All right, so if I say coming in across this boundary is 50 watts. What is that? Q. Q is 50 watts, right? All right, and it's steady state. This is my, maybe I should have used a dashed line. That's my control volume. So it's got this outer boundary where the heat is flowing out. This is the inner boundary where heat is flowing in. What is the Q on the out versus this is the in? But I didn't tell you that this is, you know, R of 2 centimeters, and this is the R of, 9 centimeters. Okay, now I clarified. Now I know this R is 2 centimeters, this other R is 9 centimeters. What's the Q out in this problem? 50. Okay, now I'm going to tell you that it's 12 p.m., blah, 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 and this is when I need my answer. What's the answer? 50 watts. The person asking the question has a green shirt on today. You know, does that change the answer? No. Is it a function of R? Could I have made a smaller control volume and said my control volume is here? 50 in, 50 out. So, is it a function of R?
No.
No. So now we grade it. And the answer is what? It's a constant. Q is constant. Radial going out. It's just a constant. So if this is a constant right here, and area is not a constant, then this dTdr is not a constant, but the product of area times dTdr has to be a constant. K is a constant, right? We're not changing the material. It's constant uniform conductivity of the material, all right? All right. Oh, well, let me do this. Let me try to press forward here. So when you take that solution for T as a function of R, you can differentiate it. You can then stick it into the equation, and you know what the area is, and you can boil down. Yes, this is another 4-letter word. A little bit of work. I know you can do the algebra. Take your time, do it. And you'll find that the Q is equal to the T1 minus T2. I've written it as if T1 is high, so it's a positive temperature difference driving the flow of heat, divided by R, where the thermal resistance is the natural log of the R outer divided by R inner, the radius is. And it's divided by 2 pi K, and then that L. L is that length of the pipe. So if it's 1 meter, great. 3 meters, fine. 20 meters, fine. Okay? So that's your thermal. And this is a big result for this section. It tells us what the thermal resistance is. Radially going out through a layer of insulation. The conductivity of the insulation is known, K. The outer radius, R2, inner radius, R1, and the length. There you go. All right. Well, you can do this. Yes, sir.
So for the area, it won't change anything if we change the length, right? For the, it will be the same, 50 all along. Right?
Okay, let me ask this question. How many people can remember how to take the derivative? Because what you have to do is this is dt, this is t as a function of r, and I'm going to take the derivative of that t as a function of r and stick it into this equation. And maybe you're looking at it saying, it doesn't look like I'm going to get a good result. So here's a question for you. What is the derivative with respect to r of the natural log of r divided by r1? That's probably the hardest part of the whole thing, right? So this is r divided by r1, the natural log of r divided by r1. All right, budding mathematicians, I'm going to pause, de-mic, walk around, work it out on your paper. So when you see that term work, sometimes you have to go and refresh your memory, and that's what we're doing here. Somebody, can you remember what is the natural log of r divided by r1? Is that the natural log of r minus the natural log of r1? All right. Somebody says, I remember the natural log of x, and I remember how to take the derivative with respect to x of the natural log of x. What was that? The derivative? 1 over x. Aha! Those two pieces of information put together allow you to come in and say, this is 1 over r. See? Now, I think this is where you were getting with your question. You have this term right here. It's going to have a 1 over r in it. And now this is an r. They multiply. You got a constant. The math does work. It's a little bit of work to make it work, but it works, okay? All right. You do the same thing now in your other favorite coordinate system. It's the spherical. But what's our governing differential equation? 1 over r squared derivative with respect to r of r squared derivative of t with respect to r. That's equal to 0. And we have that temperature at R1 is equal to T1, and the temperature at R2 is equal to T2. Here's a picture of some spherical tanks. They're going to be well insulated. They're holding something probably really, really cold or really, really hot. And they're trying to reduce the heat transfer between the substance inside the tank and the surroundings. Okay. Well, you have a well-posed mathematical problem with a little bit of, you can get the temperature as a function of r. After you get the temperature as a function of r, you want to get dt dr. Why do I want the derivative of the temperature profile? Because I put it into Fourier's law, minus Ka dt dr, and I should get a constant Q through the system. And that constant Q through the system should boil down to T1 minus T2. The way I've written it, the inside is hot, the outside layer is cold, divided by some thermal resistance, and it's a little bit of WORK. The whole thing is all just a bunch of work. You get that this thermal resistance is 1 over R1 minus 1 over R2. Divided by 4 pi k for a spherical tank. It is definitely doable. Every heat transfer textbook has this result in it. Okay? All right. Now, let me ask a clicker question. This area right here, this is a spherical tank. Is that area the 4/3 pi r cubed, or is it 4 pi r squared, or something outer? No, other. O-T-H-E-R. Answer A, answer B, or answer C. I'm looking for the equation for the area of a sphere. Is it 4/3 pi r cubed, 4 pi r squared? Because I'm going to have to use that right here, aren't I? Don't I have to use it right there? Very good, right? Somebody says, hey, I thought it was this. What is this? Volume. Look at distance, the radius cubed, meter cubed, volume, natural units. Just check. Units won't always tell you if the answer is correct. It'll just help you detect a wrong answer at times or see if there's a problem. So anyway, this one doesn't work just by the units. And then it's like, was my memory correct? Is it 4 pi r squared? Yeah, it is. Good memory. So then a little bit of work and you get this result. Well, here is in a table in our textbook, table 3.3, and it has the L over Ka for a planar wall. the natural log of R2 over R1 divided by 2 pi KL. That's for a cylindrical wall or layer or of insulation typically. And then for a spherical, you get this big result. So this is the bottom line, so to speak, the most important part of the table. But if you're interested in it, you can get the temperature distribution for all those cases and the heat flux as well as the heat rate, the rate of heat transfer. But in all of them, the Q is equal to delta T divided by R for the slab, for the cylindrical wall, and spherical layer. Okay. Can you take and put these in series? Sure. Can you couple it with convection? Sure. So let's solve this problem. Hot water flows through a 3 centimeter diameter thin-walled copper pipe. And it's wrapped with 2 centimeters of insulation that has a given conductivity. The water temperature is 80 degrees C. It has a convection coefficient of 3,500 watts per meter squared degree C with the pipe. And air surrounds it at 25 C with a convection coefficient of 20 watts per meter squared. Calculate the rate of heat transfer per unit length of the pipe. So this is going to be Q per unit length. So naturally, I try to make some sketches. I think about the convection on the inside, convection on the outside, and it's thin-walled, so I don't have any thickness for the copper. But I have the temperature on the inside, which is the same as the copper temperature, and then the temperature on the outside, which is close to 20 degrees C. But here is our temperature fluid far away on the outside. What is that, 20 degrees C? And then this is the temperature of the fluid on the inside, which is 80 degrees C. So T1 is going to be close to 80, and T2 is going to be closer to 20 than it is to 80 or whatever. It's going to be, depending on the values of H's, how close they are. Okay, so you set up a thermal network. This is T1, unknown temperature, T2. This is temperature of the fluid on the inside, 80 degrees C. Temperature of the fluid on the outside, 20 degrees C. Okay, so what is this resistance? 1 over H on the inside, area on the inside, 1 over HA. This resistance, 1 over H on the outside, area of the outside. Quick question, not a clicker question, but just a question. Are those two areas the same?
Yes.
Okay, what is the equation for the area on the inside? 2 pi r inside length. And what's the area on the outside? 2 pi r outside length. So we come over here, we had a 3 centimeter diameter. So what's the r on the inside? 1.5 centimeters, half the diameter. And it had a 2 centimeter thickness of insulation. So this thickness of the insulation is 2 centimeters. What is the R on the outside? 3.5 centimeters. So it's like you're going to pick L to be 1 meter, and then you know that, oh, basically my answer is because I began with the pick of 1 meter for the length. The 2 and the pi and the 2 and the pi are the same. Is R inner equal to R outer? No. Is the area inner equal to area outer? No. It's not. Okay? Makes sense? Very good. So these two resistances have different H's as well as different H's. I mean H's and A's. Okay, now this one was our natural log of the R outer divided by R inner divided by 2 pi KL. Again, pick L, that will be 1 meter. And what we find is that you get an overall R, an overall R which is 2.927 degrees C per watt. And when you go back and evaluate, this is like 0.1% due to the convection on the inside, and about 92% conduction through the insulating insulation. And then this was about whatever 8% or 8% for the convection on the outside. So you get a sense of the magnitude of those three components. Once you have this, then you get that this is equal to delta T divided by R. And you plug in your delta T, 80 minus 20, that's 60 degrees C. And you get that Q prime is 18.8 watts per unit length meter. Make sense? Okay. Very good. That help? Let's press forward. Now that we're experts for steady state conduction through a cylindrical wall or a spherical layer or a slab in Cartesian, let's move now to thermal energy generation. So we'll start with Q dot being non-zero in a slab. Our favorite slab coordinates is to put the center line at x equal to 0. And so we go out a positive L and then a negative L. So x is a coordinate direction going from negative L to positive L. So our slab or wall thickness is 2L. All right. And we would plot temperature in the y. Maybe we put the surface temperature, TS1 here. Maybe put TS2 there. And if there's no Q dot, it'll be just a flat line across. But as Q dot increases, what's going to happen? The temperature in the middle is going up and up and up. And this is the direction of increasing Q dot. Where is the maximum temperature? In the middle. As long as the two surface temperatures are the same, the two boundary temperatures are the same, this will be the T max right in the middle. So what we want to do is we want to find this T as a function of x. It's going to be a quadratic. It's going to be our old friend. It's like y is equal to ax squared plus bx plus c. Somebody says, plot that. I've done enough of it. That's a quadratic equation. Concave up, concave down, right? Yeah. So we're going to get this back as our solution. We're going to get that. Okay, how do you get that solution? You start off with a governing differential equation. What's it look like? Second derivative of temperature with respect to x squared equal to minus, because I put the Q dot on the other side, and I have a divide by thermal conductivity. We worked hard in Chapter 2. That's got to come from Chapter 2. That's our governing heat equation. It's second order in space. I need two boundary conditions. So the temperature at x equal to L plus L is equal to TS2, and temperature at minus L is TS1. TS1 to TS2. You can do this where they're not the same TS's. Right? You can let one be higher than the other. All right. What is our favorite four-letter word for this class? You can do it. Maybe not with me staring at you, but given a little time, you say, oh, how do I do this? Separate, integrate twice, get constants of integration, and work out the solution. I think I have the solution on the next slide. Can I show it to you? There it is. So you get the temperature at any location x. X goes between what? Negative L and positive L. And TS1 is the temperature at negative L, the specified surface temperature. TS2 is specified at positive L. There is TS2 and TS1. Look at this term right here. That's just a constant. You know, if their TS1 is equal to TS2, that's just TS. Okay, so this is my C term. Then I have a BX term. What's my B? Right? Isn't that my B coefficient? When would B equal to 0? When would B equal to 0? when TS1 is equal to TS2. Isn't that equal? Doesn't that give me the coefficient B equal to 0? It'll be now symmetric. The maximum will be right at x equal to 0. Okay. And then what is, actually this is more than just a constant. This term contributes also to the constant. So the constant term is TS1 plus TS2 divided by 2 plus Q dot L squared divided by 2K. This part comes over, contributes to this constant. Okay, but what about my x squared term? Let me make some room right here. Don't I pick up a Q dot L squared divided by 2K L squared with a minus? Isn't that my A? Do you see that? AX squared plus BX plus C. That's my quadratic. What about the A? Is it positive or negative? Negative. Do I take my hand and I have it, this is the way I kind of learned concavity. Do I point my thumb and my finger down? Or do I point my thumb and my finger up? Concave up, concave down. Negative A, concave down. I'm getting a maximum. And so if you just go back to our favorite equation, AX squared plus BX plus C equal to Y, you had the roots, X roots. That's equal to minus B plus or minus the square root. What was our quadratic equation? B squared minus 4AC divided by 2A. Okay. And that tells me where it crosses through the x-axis, where y is equal to 0. And then the other one is x max or min. It's the max or min. That's equal to negative b divided by 2a. Just old review of quadratic equation. Okay. So you go back and you can start plotting these. Let's say I plot a new one, and this time TS1 is very high compared to TS2. Here's my center line. What does the profile look like when I have heat generation? It'll be something like this, right? It's quadratic, but where's the maximum located? It's located not at x equal to 0 anymore, right? This is be x equal to 0, negative L plus L. It's going to be located at x less than 0. And if I switch it around and let TS2 be high compared to TS1, it shifts it. Okay. Now that we've solved it for a slab with heat generation, let's take a look at a rod. Well, a rod is sometimes we're getting lost with the geometry. So we're interested is as a function of r going from 0 out to the surface. So r goes between 0 and r naught. Okay? It's a solid rod. Before we were doing a layer of a insulation around the pipe. Here it's a solid rod. And we're going to be doing the same thing. L is the depth that way. Okay, but it's hard to show. So I draw it like this. There's my R going from 0 to R naught. I want to solve and find T as a function of R when I have Q dot inside heat generation. Okay. Well, what's my differential equation? 1 over R, derivative with respect to R of R, derivative of T with respect to R, equal to minus Q dot divided by K. I need two boundary conditions. One will come at the location R equal to 0. Maybe I plot it like this. I show it like this and this. This is my temperature. If I come out here, this is my TS. Where is my maximum going to be? The maximum is going to be at the location in the center. But I don't have a specified temperature boundary condition. I have a symmetry boundary condition such that the derivative of the temperature with respect to R at R equal to 0 is equal to 0. Where did that come from? From symmetry. You got to get that boundary condition correct. So the slope of this profile right here, it's flat at R equal to 0. The derivative is 0 there. Okay. Then the other one is that T at R naught is equal to TS. A little bit of work, and you can solve for the temperature distribution in that rod. So the temperature distribution, T as a function of R, is equal to the surface temperature plus Q dot R naught squared divided by 4K 1 minus R over R naught squared. What does that function look like mathematically? Oh, exponential function. No, good try. Hyperbolic cosine. No, good try. Ratio of polynomials that are to the nth power. No, really simple. It's a quadratic. It's just a quadratic. It's pretty easy to plot. Here's a sketch of one right there. All right. So where's the maximum at? At R equal to 0. What's the value of the maximum? The surface plus Q dot R naught squared divided by 4K. That helps you get the maximum temperature right away. All right. Ready to solve this problem? We have a long, solid, 2 centimeter diameter rod. So the radius of this solid rod is 1 centimeter. And it has a thermal conductivity given, K is given, 7.2 watts per meter degree C. Has a uniform heat generation of 1.7 times 10 to the 7th watts per cubic meter. And the outside surface is given, TS is equal to 80 degrees C. Calculate the maximum temperature in the rod. Can I pause and let you do it? What's the maximum temperature in the rod? I'll walk around and check a few answers. So I'll just pick it up here. What we have is we have the solution of the temperature profile, and then if you're interested in the maximum, you just have to put in the Q dot, put in the R naught, square it, divide by 4K, add to it the surface temperature, and you'll come up with the T max is about 139 degrees C. That's all it was, plug and chug. But now we change it up a little bit. You have the same solid rod with the same thermal conductivity and the same magnitude of heat generation inside of it. But instead of having the surface specified to be 80, you have a fluid around the rod specified to be 80 degrees C and a convection coefficient. So maybe I kind of draw radial going out. Here is R naught, starts at 0, and we're going to plot temperature in this other direction, dimension T. And right here, we don't know what that temperature of the surface is, TS, and we're trying to find T max right there. But we're given that the fluid temperature, way out here, T infinity, is equal to 80 degrees C. So it kind of goes like this, and then there's abrupt change. And then what do we have in here? We have something like that, and it's flat. It's quadratic in the rod. And from the boundary condition, it's flat. So how am I going to calculate that maximum temperature in this case? Should I give you a few minutes to work it out? Out here we have the convection on the outside of the rod with a convection coefficient of 9,100 watts per meter squared degree C. Let me pause, walk around. Well, I wish I'd give you more time, but let's go ahead. If I had Q dot and I multiplied by the volume of the rod of interest, would that be how much heat was being given off? And what I'll typically do is I'll say, okay, this rod is like this, and what is its radius? That's R naught. That was equal to 1 centimeter. The diameter is 2 centimeters, 1 centimeter. So the volume, Q dot, the volume is going to be pi R naught squared times L. And I like to just say L is picked to be 1 meter. Or you can divide over and then everything's per unit length. All right? So this will cough up how many watts have to get off of the surface and into the fluid. All right? Then I come over and I say, what is my rate equation out of chapter 1 to get off of the surface and into the fluid? It's called Q is equal to HA TS minus T infinity. In this equation, I'm looking to solve for TS, the surface temperature. But this one is my 80 degrees C. My H is my 9,100. And the Q is there. What about this area? This area right here. It's that outer convective area, this outer surface area. Is that 2 pi R naught L? Is that what that is? 2 pi R naught L? Sure. And so, again, that L picked to be 1 meter. Then remember, we're doing everything per length of 1 meter. So this allows me to calculate TS. TS is equal to T infinity plus Q divided by HA. Notice if you wanted to, T infinity is equal to Q, which is Q dot pi R naught squared L divided by the H and then the A, pi R naught L. Notice that the L's, if you work in symbols, will cancel out. This R goes, that pi goes, so you can get it reduced a little bit there. And so, let me clean this up a little bit. What's that equal sign? That's plus. So the temperature surface is T infinity plus Q dot R naught divided by H. When you run the number, does it come in around 89.3 degrees C? Yes? Okay, got a few confirmations. Now that I have that, I just go back to the previous problem where temperature max is equal to the surface temperature plus, what was that, Q dot? And then we had Q dot R naught squared divided by, that's a bad looking Q, Q dot R naught squared divided by 4K. And we just solved for TS, so we get the T max is 148 degrees C. Looking into the future, next time we pick up heat transfer from extended surfaces. So please read ahead, stay up to date.